the full wave rectifier. So full wave rectifier, see the diagram, you will have two SCR. See, if this SCR is not there, it's going to be half wave rectifier. So here, if you have one more rectifier for the bottom half of your secondary of transformer, you are going to have one more SCR. It is going to be called as full wave rectifier, and these two SCRs will have a common trigger circuit. And we are going to see what is the operation of the circuit. So it is exactly similar to an ordinary full wave rectifier, except see, conventional rectifiers, instead of SCRs, you have diodes. So instead of SCRs, you will have diodes in conventional rectifier, but I'm replacing SCR diode with SCR because I have the option to trigger the circuit whenever I need it. I don't want the circuit to be always on. I need to trigger my circuit whenever there is a need. So that is why I'm going to replace all the diode by SCR. If you have one SCR in the secondary of transformer, you call it as half wave rectifier. If you have a pair of SCRs, you are going to call it as a full wave rectifier. So see here, you have a pair of SCRs having a common trigger circuit, and the center trap transformer, you have the center of the transformer is grounded. Okay. So now we are going to see the operation. So angle of conduction, you can adjust it by adjusting the gate current. As you know, if you adjust the gate current, you can accordingly change the angle of conduction. So during the positive half cycle of the input signal, SCR1 is active. So during the positive half, what happens? This SCR is given positive voltage, and this SCR is given negative voltage. So the SCR1 is going to conduct, SCR2 is going to be off. Okay, so during the positive half, after a firing angle theta, this SCR1 is going to conduct till half cycle, till the complete half cycle is going to complete. Okay, so I'm talking only about the positive half cycle here. So during the positive half cycle of my AC input given to the transformer, in transformer, since you're going to have a center trap transformer, the upper and lower windings will be of opposite polarity. So during the positive half cycle, the upper winding will have a positive voltage, and the lower winding will have a negative voltage, and SCRs will work with positive voltage. So this SCR will be on, this SCR is going to be off. So it will work after a conduction angle theta till the completion of my positive half cycle. Okay, that is for the positive half cycle. So whenever the voltage is going to reach V1 only, SCR is going to start conducting, and that's why the shaded portion indicates the conducting part of your SCR. The negative half cycle, what happens? During the negative half cycle, this voltage becomes negative, this becomes positive. So what happens? This SCR will not conduct, and this SCR will conduct. So during the negative half cycle, this SCR2 is going to conduct, and same way it is going to conduct only after an angle theta till the waveform reaches V1. So it will conduct from that point V1 till the completion of the cycle. So in this way, what happens during the positive half cycle and during the negative half cycle, both the SCRs will conduct in alternate fashion, giving rise to output. So the main advantage of this circuit over conventional full wave rectifier is, since you are having the diodes are being replaced by SCR, you have this controlling option in the form of trigger circuit. So you can adjust this value of theta for how much percentage of the input waveform my SCR has to conduct. So I can tune that accordingly. So only that feature is available only in SCR. It is not available with conventional PN junction diode. That's what they have given. See here, the main advantage why this full wave rectifier is going to be highly effective is I can control the firing angle by using proper gate current to the SCR, whereas that controlling factor is absent when you're going to use PN junction diode. Okay, so that is the explanation. And now the same calculations, the average voltage you find, it is same thing, same formulas you find, and this is double it is 2 times of the half wave rectifier, right? So negative cycle are also getting rectified, and the SCR, so this value is going to be 2 times of that. So if you put theta is equal to 0, you will get the value as 2 Vm by pi, whereas it was Vm by pi. See here, when I put theta equal to 0, I get Vm by pi in a half wave rectifier. So in full wave rectifier, see here, the final answer for V average, Vm by pi into 1 plus cos theta. When I put theta equal to 0, I get the answer as 2 Vm by pi. So it is 2 times the value of It is 2 times the value of half-wave rectifier. So they say that this SCR full-wave rectifier, which is designed using SCR, is going to be more efficient than your half-wave rectifier. There are applications where only half of your wave has to be rectified and the remaining wave should not be rectified. So in that case, I can use either half-wave rectifier or full-wave rectifier depending on my requirement. There is no hard and fast rule that only this rectifier has to be used and that rectifier need not be used. So that rule is not there. So depending on applications, you can see which rectifier has to be incorporated into your application.